Hi, I'm Brandy Heflin. I'm a personalized physics instructor, and I help high school and college students feel confident and successful in learning physics. Welcome to my AP Physics exam preparation video series. Over the next several weeks, I will be releasing a sample free response question from each of the 4 AP Physics exams so students can familiarize themselves with how the questions will be asked and how the exam will ask students to demonstrate their knowledge. As a tutor working with students all over the country, I know that not every student has the opportunity to work with released exam materials prior to exam day, and this video series is intended primarily to help those students. So AP Central describes for the AP Physics C Mechanics exam an experimental design or lab-based component question and discusses that all 3 questions will assess all 7 of the science practices listed here. This video will cover C Mechanics 2016 question 3, which dealt with rotational dynamics, angular momentum, and uniform circular motion. A uniform rod of length d has one end fixed to the central axis of a horizontal frictionless circular platform of radius r equals 2d. Fixed at the other end of the rod is an ideal spring of negligible mass to which a block is attached. The block is set in frictionless grooves so that it can only move along a radius of the platform as shown in figure 1 below. The equilibrium length of the spring is d over 2. Below is a table showing the mass of the block and the masses and rotational inertias of the rod and the platform. The block has mass m, the rod has mass 3m, and the platform has mass 5m. The rod has rotational inertia of its mass times d squared divided by 3 about the end of the rod, and the platform's rotational inertia about its central axis is its mass times r squared divided by 2. A motor begins to slowly rotate the platform counterclockwise as viewed from above until the platform reaches a constant angular speed omega. Under these conditions, the spring has stretched by an additional length d over 2 as shown in figure 2. Answer the following questions for the platform rotating at constant angular speed omega. Express all algebraic answers in terms of m, d, omega, and physical constants as appropriate. Part A. Derive an expression for the spring constant of the spring. So the first thing we're going to need to recognize is that, and give me just a moment to grab my pen tool, we're going to need to recognize that the spring is providing a centripetal force on the block. And we will also need to remember that this will be equal to the mass of the block times its centripetal acceleration. And we need that because we're going to have to express everything in terms of r and omega, so our usual v squared divided by r isn't going to cut it. Okay, so our spring force is equal to kx, where x is the stretch of the spring, and then our expression for the centripetal acceleration will be r omega squared multiplied by the mass of the block, which of course was an m. So our spring, we were told, had a rest length of d over 2, and then it stretched by an additional length d over 2. And then the radius of the path that the block is following is 2d. So with all of our substitutions, we have k times d over 2 equals m times 2d times omega squared. So when we solve this for k, we are left with 4m omega squared. So let's talk about scoring. We're going to get 1 point for indicating that the spring force equals the mass times the centripetal acceleration. We're going to get a point for correct substitution for x. And our final point is going to be for correct substitution for r in an equation that can be used to solve for k. Let's clean that up, make that look a little bit more legible. That almost looked like a D. There we go, to solve for K. So that's our 3 points for this part. Part B1, determine an expression for the rotational inertia of the block around the axis of the platform. For this part, we're going to need to remember the relationship for the rotational inertia of a discrete particle, which is going to be, or a collection of particles, which is the sum of m times r squared. And in this case, we have just the single block m, and the radius of its path, the distance from the rotational axis, is 2d, which we'll have to square. So the rotational inertia for the block will be equal to 4m times d squared. And we get 1 point here, and that is for a correct answer or an answer consistent with the radius used in part A. And this is a really common way that the exams are scored. If you make a mistake on an earlier part, let me actually fix that. If you make a mistake on an earlier part and then use that incorrect value or equation correctly later, they set up the scoring so that you can get full credit on the later part using the mistake, instead of penalizing you twice. Part 2, derive an expression for the rotational inertia of the entire system about the axis of the platform. Fun, fun. So for this one, the rotational inertia of the system is going to be equal to the rotational inertia of the platform plus the rotational inertia of the rod plus the rotational inertia of the block. So back on our second slide or so, we were given that the rotational inertia of the platform is its mass times r squared, capital R squared, which is its radius, divided by 2. The rotational inertia of the rod was given as mr, its mass, times d squared divided by 3. And then, of course, we have the m times little r squared for the block. And now we can substitute. Because we know the mass of the platform was 5m, we know the radius of the platform is 2d, and we'll square that whole quantity, divide by 2. We know that the mass of the rod is 3m times d squared, all divided by 3. And then, of course, we just found that the rotational inertia of the block was 4md squared. And notice that we basically have, when we factor out the md squared, we have 10 plus 1 plus 4 times md squared, and our final result is going to be 15m times d squared. So let's talk scoring here. We need an indication that the rotational inertia of the system includes the platform, the rod, and the block or object. I don't know why the scoring guidelines call it object when the question calls it a block. And then our second point here will be for substituting into an equation the rotational inertias of the platform, rod, oops. I was thinking ahead to needing to write block, and I wrote rod instead. What happened? There we go. Let's grab my pen tool rather than my highlighter. And this one is consistent with part B1. So again, if you messed up finding the rotational inertia of the block in part B1, but you used it correctly in part 2, then you can still get full credit for that. Part C, determine an expression for the angular momentum of the entire system about the axis of the platform. Well, we're going to remember that angular momentum equals rotational inertia times angular speed. So all we have to do here is substitute in our 15md squared that we found in the last part, and then multiply by omega. And this one was worth 1 point for an answer consistent with part B2. While the system continues to rotate, a small mechanism in the pivot moves the rod slowly until the center of the rod is positioned on the axis as shown in figure 3 below. The same constant angular speed omega is maintained by the motor driving the platform. Part D, derive an expression for the distance x that the spring is stretched when the rod reaches the position shown in figure 3 at right. So once again, we're starting off with this idea that the spring will be providing a centripetal force that will be equal to the mass of the block times its centripetal acceleration. Once again, kx is the spring force, where x in this case is the stretch of the spring. We happen to use x in the diagram, but in general, the x I mean here is the general stretch of the spring. And that's going to be equal to m times r omega squared as before. Well, we got a spring constant before of 4m omega squared. And as mentioned, x is actually the symbol we're using for this particular amount of stretch of the spring. So we'll leave the x there. And now that will be equal to m. Now we need to be careful about the radius of the block's path. So we have on our diagram over here, we now have d over 2 is the amount of rod that's left, plus the d over 2 that was the original length of the spring, plus the x that is the stretch of the spring. So the radius of the block's path is going to be d plus x. And now we can multiply that by omega squared. And so when we cancel out a few things, I was trying to decide if I was going to write out more of the algebra, but I realized I don't have to. So the m's cancel out on both sides. The omega squareds cancel out on both sides because it's all multiplied. And now we're going to have 4x equals d plus x. So 3x is equal to d. So now x will be equal to d divided by 3. So let's talk about scoring. Similar to the very first part, we're going to get a point for indicating the spring force equals mass times centripetal acceleration. We're going to get a point for substituting for K, or substitution consistent with part A. Once again, if you happened not to get it right when you did part A, but your substitution is consistent here, they don't penalize you a second time. Actually, make that a little bit neater. And then our final point is going to be for substituting for R into an equation that can be used to solve for x. For parts E, F, and G, assume the center of the rod is still moving toward the axis of the platform. Part E is the angular momentum of the entire system increasing, decreasing, or staying the same. You have your 3 choices and then justify your answer. So my pro tip for questions like this is justify. Why am I writing second? Oh my goodness. Let's try that again. We're going to justify our answer first. Like, let's write that part out first. And then come back and make your choice second. And this is anytime it says justify your answer, explain your reasoning. And that's because you can't make a good selection of the choices until you've already thought the problem through, and this space to justify your answer is your space to do your thinking. So the rotational inertia I of the system decreases while the angular velocity omega stays the same. And because the angular momentum is I omega, it decreases. And so we'll select decreasing. And then our points here are 1 point for selecting decreasing, and 1 point for a correct justification, and there's a note here that if the wrong selection is made, no points are earned for the justification. And that's also a common thing that shows up in the scoring too, is that sometimes they, won't allow you to pick up partial credit if you didn't get one part of it right. And this is an example where, if you selected the wrong thing, then it doesn't matter if you explained your wrong answer correctly. Like if you have a justification that is consistent with increasing, you're not going to get credit for that because if you had actually answered the question correctly, you wouldn't get decreasing at all. Or you wouldn't get increasing at all, sorry. All right, and in part F, in order to keep the system rotating with constant angular speed omega, is the motor doing positive work, negative work, or no work on the rotating system? Justify your answer. And as you can see here, I've already have displayed the answer. Because the angular velocity is constant and the rotational inertia has decreased, the rotational kinetic energy has decreased. Therefore, work must be negative. So we'll check that. And here, our points are for selecting negative. And for a correct justification. And once again, there's a note for this part as well, that if the wrong selection is made, no points are earned on the justification. All right, and on the block in figure 4 below, draw a single vector representing the direction of the acceleration of the block. Draw the vector so that it is starting on and pointing away from the block. So we have both a tangential component and a radial component of this acceleration, and we're going to end up with an arrow that is down and to the right. And our final point here for this question is for an arrow starting on the box and pointing down and to the right. So I hope you have found this demonstration of an AP Physics C mechanics question helpful. If you have a video solution request for my YouTube channel, you can send it to physicsproblemrequests@gmail.com. I won't be putting any of them up until my AP series is over, though. If you would like some email assistance, you can reach me at freephysicshelpline@gmail.com. Send your question and the work you've done on it so far with a limit of 10 questions per academic year. If you'd like to know more about my online physics tutoring services, you can email me at brandyheflinphysics@gmail.com. You can visit my website, virtualphysicsofficehours.com, or you can find me on Facebook. I'm Physics Tutor Brandy. So just a few notes. AP is a registered trademark of the College Board. The College Board does not endorse or recognize this video or my services. All of the materials presented are available on AP Central at the link shown here for the AP Physics C Mechanics exam, and those materials include the released free response questions, the scoring guidelines, and sample student responses and commentary. I strongly encourage students to review those sample responses to get a feel for the different levels and quality of the responses prepared by the students who took these released exams live, and to see what the scores for that year were looking for and how they decided to award points. If you have questions, you can reach me at brandyhealthlandphysics@gmail.com. I'm physics tutor Brandy. I love physics, and I love helping you. Until next time.